Welcome to an example on how to use Stoke's theorem to evaluate a surface integral. We're given the vector field f and asked to use Stoke's theorem to evaluate the double integral over the surface S of the curl of f dot differential S, and this surface integral is often expressed in this form here, which is equivalent. Here the surface S is the hemisphere x squared plus y squared plus z squared equals 25, where z is greater than or equal to 0 and it's oriented upwards. Stoke's theorem states that if S is an oriented surface with unit normal vector n with a piecewise smooth closed boundary C with a positive orientation and the vector field F has components p, q, r, which all have continuous partial derivatives, then the double integral over the surface S of the curl of f dot n differential S is equal to the line integral along the closed curve C of f dot differential r. So this states the relationship between line integrals and surface integrals of a vector field under these conditions. It tells us that the net rotation over the surface S is equal to the net rotation on the boundary of C. So looking at our problem graphically, the vector field F is graphed here in gray. The surface of integration is the part of the sphere above the xy plane graphed in yellow, and we can evaluate the surface integral by using a line integral where the curve C for the line integral, if we looked at on the xy plane, would be this circle in the xy plane centered at the origin with a radius of 5. Notice how this curve is the boundary of the surface S. So again, by applying Stoke's theorem, the double integral over the surface S of the curl of f dot differential S, which again can also be expressed in this form, is equal to the line integral along the closed curve C of f dot differential r. So remember, to evaluate this line integral, we'll have to parameterize this curve C using the vector function r of t. Then the line integral along the curve C of f dot differential r equals the integral from a to b of the vector field f expressed in terms of t dotted with r prime of t dt. So let's work on parameterizing the curve C using the vector function r of t. Well, notice how if we set z equal to 0 for the equation of the hemisphere, that would give us the equation x squared plus y squared equals 25, which does give us the curve C. Looking at our graph here on the far right, again, here's the curve C, which is the boundary of the surface S. So on the xy plane, the curve C is this circle, where the radius is 5, and the center is at the origin. We know in the xy plane, any circle centered at the origin can be expressed parametrically as x of t equals r cosine t, and y of t equals r sine t, where r would be the radius. So in this case, for r of t, we can let the x component be equal to 5 cosine t, the y component be 5 sine t, and because the curve C is in the xy plane, the z component is 0. And notice how this circle is traced out counterclockwise when t is on the closed interval from 0 to 2 pi. This will be important later for limits of integration. Now we still need two more things before we set up this integral here. We need to find r prime of t. The x component would be the derivative of 5 cosine t, which would be negative 5 sine t. The y component would be the derivative of 5 sine t, which is 5 cosine t. And the z component is the derivative of 0, which of course is 0. And now for the last step, we need to express the vector field f in terms of t, where along the curve C, x equals 5 cosine t, y equals 5 sine t, and z equals 0. So for the x component of f, which is x squared times e raised to the power of yz, well, x squared would be the square of 5 cosine t, which is 25 cosine squared t, and then e raised to the power of yz, well, y times z would be 0, so we'd have e to the 0, which is just 1. And then the y component is x times e raised to the power of xz. Well, x is equal to 5 cosine t. And then e raised to the power of xz is going to be e to the 0 again, because z is 0. E to the 0 is 1. And the z component is z squared times e raised to the power of xy. But again, if z is equal to 0, then the z component is 0. So the double integral over the surface S of the curl of f dot differential S is equal to the line integral along the closed curve C of f dot differential R, which equals the integral from a to b, which would be from 0 to 2 pi, of the vector field f expressed in terms of t, which we have here, dotted with r prime of t, which is here, dt. Let's go and evaluate this on the next slide. So now we'll find the dot product. 25 cosine squared t times negative 5 sine t is equal to negative 125 cosine squared t sine t. And then we have plus 5 cosine t times 5 cosine t, that's plus 25 cosine squared t. And of course, 0 times 0 is 0. Now from here, I think it's best to write this as two separate integrals. Let's write this as negative 125 times the integral from 0 to 2 pi of cosine squared t sine t dt, and then plus 25 times the integral from 0 to 2 pi of cosine squared t dt. So here we'll have to perform use substitution to integrate, and here we'll have to use a trig identity, or a power reducing formula, to integrate cosine squared t. So for this integral, let's let u be equal to cosine t, and therefore differential u is equal to negative sine t dt, which means negative du is equal to sine t dt. Which means in terms of u, all of this would be negative u squared du. And for this integral, we'll use the identity cosine squared t equals 1/2 times the quantity 1 plus cosine 2t. So we can think of this as 1/2 times the quantity 1 plus cosine 2t. Integrating here with respect to u, we'd have negative u to the third divided by 3, or negative 1/3 times u to the third. So that ended up being 125 thirds. And u to the third is really cosine cubed t. Plus, and for this integral here, let's rewrite this as 25 halves times the integral from 0 to 2 pi of 1 plus cosine 2t dt. So here we have plus 25 halves times, well, the net derivative of 1 with respect to t would just be t. Now we integrate cosine 2t, we do have to perform u substitution, where u equals 2t, differential u equals 2 dt, dividing both sides by 2. Notice how dt is equal to 1/2 du. So we can think of this as 1/2 cosine u. So the antiderivative would be 1/2 sine u, which is really 1/2 sine 2t. So here we have 125 thirds times, when t is 2 pi, cosine 2 pi is 1, so we'd have 1 cubed, which of course is 1, minus, well, cosine 0 was 1, so we'd have 1 cubed, which is also 1, plus, here we have 25 halves times, when t is 2 pi, we have 2 pi, plus 1/2 times sine of 2t, which would be sine of 4 pi, which is 0, minus, when t is 0, we have 0, plus 1/2. Sine of 0 is 0, so 1/2 times 0. So simplifying, notice here we get 0, plus here we have 25 halves times 2 pi. This is 0, and this is 0. So the final result is 25 pi, which is a decimal approximation, would be approximately 78.5398. So this is the value of the surface integral as well as this line integral. So going back to our graph, the value tells us a net rotation across the surface S, which is the hemisphere above the xy plane, which also equals the net rotation along the boundary curve C, which is the circle in the xy plane. I hope you found this helpful.